All right, let's get right into it. We're about to explore one of the biggest, most mind-bending puzzles in all of physics today. It's a huge cosmic mystery that, believe it or not, all boils down to just a single number. But this isn't just any number. This is a number that seems to be challenging our entire picture of how the universe works.
And that leads us to this. This is the question that's keeping cosmologists up at night. Seriously, they're asking themselves if everything we think we know about the universe might be fundamentally wrong. Why? Because two of our most trusted, most precise ways of measuring the cosmos are giving us two totally different answers. And that little disagreement, well, it could be pointing to a crack in the very foundation of modern physics.
Okay, to really get to the heart of this problem, we have to start with the basics. Back in the 1920s, George Lemaitre and Edwin Hubble figured out that the universe isn't just sitting still, it's expanding. Space itself is stretching, carrying whole galaxies along for the ride, kind of like raisins baked into a rising loaf of bread.
So how are we going to unpack this whole mystery? Here's the game plan. First, we're going to look at the basic rule for how the universe stretches. Then we'll put on our cosmic detective hats and check out the two different measuring tapes scientists are using. That's when we'll find the two numbers that just don't add up. After that, we'll look at a really surprising clue from some of the most bizarre objects in the cosmos before we finally ask the big one. What does all this mean for our understanding of, well, everything?
All right, first up, let's talk about the fundamental rule of cosmic expansion.
And that rule is the Hubble-Lemaître law. It's actually a pretty simple and incredibly powerful idea. All it says is that the farther away a galaxy is from us, the faster it appears to be moving away. In that little equation, v is the galaxy's speed, d is its distance, and h is the magic number, the Hubble constant or h0. Think of it like the universe's current expansion speed. And it's the exact value of that number that's causing all this trouble.
So, if we need to measure the Hubble constant, how do we actually do it? Well, it turns out there isn't just one way. Cosmologists have come up with two incredibly precise but totally different cosmic measuring tapes.
You can think of it like two teams of detectives trying to solve the same case. On one side, you've got the early universe team. They're looking for clues from the dawn of time itself. And on the other side, you've got the late universe team. They're measuring the scene as it is right here, right now. And here's the kicker. Both teams are absolutely brilliant at what they do.
So the early universe team starts with this, the cosmic microwave background, or CMB. This is literally the leftover glow from the Big Bang. By studying the patterns in this ancient light and plugging them into our standard model of the universe, which is kind of like our master recipe for the cosmos, they can fast forward 13.8 billion years and predict what the expansion rate should be today. It's an incredibly powerful calculation based on everything we know about physics.
Now, the late universe team does things totally differently. They're way more direct. They built something called a cosmic distance ladder. They start by measuring the distance to nearby stars called Cepheids, which are amazing because they pulse like cosmic heartbeats, and the rate of the pulse tells you their true brightness. They're like light bulbs with the wattage printed right on them. Then they use those known distances to calibrate even brighter beacons farther away, like Type Ia supernova. These are exploding stars that all have the same predictable brightness. By seeing how dim they appear, we can figure out exactly how far away they are and measure the universe's expansion rate right now.
So we've got these two gold standard methods. One predicts the number based on the baby universe, and the other measures it directly in our backyard. In a perfect world, they'd give us the exact same number, right? Well, they don't.
I mean, you have a prediction based on the dawn of time, and you have a direct measurement from today. They absolutely should match. The problem is, they don't. And we're not talking about a small difference either.
The early universe team, using that afterglow from the Big Bang, comes up with a Hubble constant of about 67 kilometers per second per megaparsec. Now don't worry about the units. A megaparsec is just a ridiculously big unit of distance. Just remember the number, 67.
But then, the late universe team, the ones measuring supernovae in our cosmic neighborhood, gets a completely different answer, about 73.
So here's the crucial part. This is not a rounding error. This gap between 67 and 73 is what scientists have dubbed the Hubble tension, and it is statistically significant, which is a sciencey way of saying it is extremely unlikely that this is just some random fluke. Something is off.
So what do you do when your two best methods disagree? You bring in a third, completely independent judge to break the tie. And that's where things get really cool, involving something called quasars and a little help from gravity. First off, what even is a quasar? Just think of it as an insanely bright cosmic lighthouse in the super distant universe. They're powered by giant black holes, and they're so bright we can see them from clear across the cosmos. And for our story, the important thing is that they flicker.
Now this is where it gets wild. Sometimes, a huge galaxy gets right in between us and one of these distant quasars. And, just like Einstein predicted, the massive gravity of that galaxy acts like a giant, natural lens in space. It literally bends space-time, and it splits the light from the quasar into multiple paths. So when we look from Earth, we end up seeing several images of the exact same quasar.
This whole setup allows for a truly ingenious technique called time delay cosmography. You see, when the quasar flickers, the light from each of those lensed images has to travel a slightly different path to reach our telescopes. That means the flicker shows up at slightly different times for each image. By measuring that tiny time delay, scientists can do some clever math and figure out the distances involved with incredible precision. And from that, they can calculate a completely independent value for the Hubble constant.
And don't just take my word for it. As researcher Frederick Corbin puts it, this method is pivotal because it's totally separate from the other two. It doesn't need the cosmic microwave background, and it doesn't need that tricky distance ladder. It's a completely fresh set of eyes on the problem.
So, the big moment, the tiebreaker. What did the quasar say? Well, this powerful independent check agrees with the higher value, the one around 73. So instead of solving the puzzle, the quasars just made it worse. They've basically confirmed that this tension is very, very real.
Which brings us to the final and maybe the most profound part of this whole story. Why? Why does this one number cause such a crisis? Why does anyone care?
They care because the expansion rate is tied directly to what the universe is made of. And as you can see from this little cosmic history chart, those ingredients have changed over time. Early on, gravity from matter and radiation was putting the brakes on expansion. But today, some mysterious thing we call dark energy is hitting the accelerator. So, if the expansion rate today is different from what our models predict, it could mean our recipe for the universe, our understanding of dark matter and dark energy, is missing a key ingredient. And that's the bottom line. That's what's at stake. If the Hubble tension is real, it's not just some small error in a calculation. It could be the first real crack in our standard model of cosmology, the theory that has guided physics for decades. It might force us into what one source called a profound rethinking of everything we thought we knew about the cosmos. So, we're left on a thrilling cliffhanger. The universe is practically screaming at us that we've missed something that might be completely new, lying just beyond our current theories. And the quest to solve this tension isn't just about finding the right number anymore. It's about discovering what new, incredible physics this whole cosmic puzzle is just waiting to reveal to us.